You let me know when.
Yeah, you can start.
Hello, everybody, to the Analytics for a Better World Research Seminar. It's a privilege to introduce Zan Pauphilet. Zan is an assistant professor of management science and operations at the London Business School. He graduated from MIT a few years back. It's one of my pride moments to say that he was a doctoral student of mine. Zan has done unusually broad and deep work in a variety of areas, both in various areas of optimization, but as you will hear from today, and as in other areas in analytics for a better world and their combination. It's a rare combination, especially among young people, to find people like Zan who are strong, very strong in all aspects of operation research. He has received many awards, including the George Nicholson Award for Best Student Paper, the Computing Society Best Paper Award as well, and many others. Prior to MIT, he was in École Polytechnique, and in addition to what you will see today, he has worked in addition to other theoretical aspects of operation research. He also worked in many other ABW projects, several of which might be appropriate for future presentations. But today, he will be talking about a topic that I find very exciting, about the cleaning the oceans. Zan, the floor is yours.
Thank you very much, Dimitris, for the kind introduction, and thanks also, Dick, for organizing this webinar. So today, I'm very excited to be presenting this work about, as Dimitris mentioned, using optimization to help improve the efficiency of ocean cleaning, especially removing plastic from the ocean. So to start with, I would like to acknowledge that this is a collaboration actually facilitated by ABW between a Dutch NGO, that's the Ocean Cleanup, and I'll talk about it in a bit. And on the academic side, so it's primarily driven by London Business School and the University of Amsterdam. It's a joint work with Dick Den Hertog, and also, most importantly, with gyres, who's my PhD student at LBS. So that's to put faces on those names. So Bruno and Yannick are our main collaborators from the ocean cleanup side. And as I said, most of the work I'll be showing today is thanks to the great work of gyres, who's correctly put in the middle, in the center of that slide. So the issue I'm going to talk about today is ocean pollution, okay? Ocean pollution is a very important problem. It's actually 80% of that is plastic, okay? So you can pollute the ocean in many different ways, but 80% of ocean pollution actually comes from plastic waste, okay? And that represents around 8 to 10 million metric tons being wasted in the ocean every year, okay? So that's, of course, as the previous picture was showing, hard to marine life, all the ecosystems in the ocean. Oceans are a very important, system that helps us regulate global temperatures, and also it has an impact on human life, okay? Oceans are a very important aspect and a very important place for a lot of economic activities, fishing being one of them, but also tourism. And actually, it's been estimated that the economic cost of plastic pollution in the ocean is estimated to be around $6 to $19 billion per year, okay? So it's a very important problem with a lot of consequences, not only from a biological perspective, but also from an economic perspective. And that's also one of the reasons why, hold on, I can't see. Yeah, that's also one of the reasons why it's actually one of the Sustainable Development Goals set by the EU, the UN. So the SDG number 14, the first mission in this Sustainable Development Goal is to reduce ocean pollution. So to tackle this challenge, we're going to partner with the Ocean Cleanup, which is a Dutch NGO founded in 2013, whose mission is to clean up oceans from plastic. Okay, it's very easy to say, right? Harder to do. And basically, to tackle this issue, there are two aspects you need to address, two activities. One is the cleanup activity, and the other one is what they call at ocean cleanup, the interception. Cleanup means removing legacy plastic from the oceans, okay? So plastic, as I said, 8 to 10 million tons of plastic have been thrown in the oceans every year for a long time, and this plastic accumulates in our oceans. So a first goal and objective is to remove this legacy plastic, remove this floating plastic from our ocean. The second way to tackle this problem is to prevent plastic from being wasted in the oceans altogether. And so, for example, on that regard, the Ocean Cleanup has estimated that there are 1,000 rivers in the planet, on Earth, that are responsible for 80% of plastic pollution coming from rivers in the ocean. Okay, so that's also something they're looking at, even though today what I'm going to be mostly be talking about is a partnership where we help them achieving the first goal, which is removing this legacy plastic from the oceans. So to show you how they do that, or the way they thought about approaching that problem, I'm going to show you a quick video of the system they have developed.
So Jenny is a 800-meter long floating barrier which we tow through the water. The barrier is 3 meters deep in the water. It's completely open at the bottom, which is important because it allows fish to escape. And it has flotation along the top, which helps it to keep. And it's connected at each end to one of these vessels, the one that I'm standing on here, and also the vessel that you can see behind me. Those vessels are moving ahead at a very slow speed. It's about 1.5 knots, which is less than 2 miles an hour. As we move through the plastic and through the water, then you get a natural flow of water caused by that movement, and the plastic is carried along those two barriers, which we call wings, on each side, and it's transported to a central area, and there's a collection area, which we call the retention zone, in the middle of that U shape. So all of the plastic flows along, it flows into that retention zone, and that enables us, after a certain time, maybe once a week, to bring the two vessels together, hand one wing of Jenny to the other vessel, so they're holding both, and the other vessel can go around to the back of the system and pick up the retention zone, which has all the plastic inside. Then we take the plastic from the retention zone, empty it all out onto the deck. We separate it into different materials according to different recycling streams. We package it up and we take it back onto shore, and then we can send it for recycling.
So that's, I think, a perfect illustration of the problem we're going to study today. They have developed this massive system, what we'll call the system, which is basically a massive fishing net to fish plastic instead of fishes. It's dragged by two boats that you can see on this picture. It's kind of a U-shaped net, and here in the center you have a retention zone where all the plastic that you catch gradually accumulates. And from time to time, this has a fixed capacity, and you empty that, and that's how you collect the plastic out of the ocean, okay? So they've developed this technology, and they're actually still developing this technology. They're thinking a lot about how to design such a system. So here on this picture, think of this distance as 800 meters, and they want to go all the way to 2.5 kilometers. So the Ocean Cleanup is constantly working on, developing this system to make it more efficient and bigger. But the question we're going to look at today is, can we help them navigate this system in the ocean? And so the good news is there are what are called ocean gyres. Those are big circulating currents that make plastic accumulate. So basically, plastic is being wasted in ports mostly, and other areas at the coast level. And those currents create accumulation zones around the globe. There are a total of 5 such patches, okay? And the biggest of them is the one we're going to be studying today, the Great Pacific one, Great Pacific Garbage Patch, GPGP. So that's actually good news from an efficiency perspective, because if your objective is to remove this legacy plastic from the seas, the first place you should start to look at is those accumulation zones, okay? Because those are the places where you'll have the highest plastic density. So here we're going to look at one such gyre or patch, which is called the Great Pacific Garbage Patch. As you can see, is in the North Pacific. And because of those circulating currents, there are two main accumulation areas. And the one we're going to be looking at today is the one that's halfway roughly between Hawaii and California. Okay. It's a big zone. Okay. It's about twice the size of Texas, 3 times the size of France. And they estimate that there are 80,000 tons of plastic in that area. Okay. Actually, all the numbers I give here, you know, it's actually a very active field of research in terms of in environmental sciences to document actually how much plastic there is in those areas. And actually, the latest estimate before this one was 4 to 16 times lower, 4 to 16 times lower. So actually, the ocean cleanup, in addition to developing this system, they contribute a lot to the research that's documenting how big of an issue is that and the quantity of plastic that is actually being wasted in the oceans and that converges to those accumulation zones. Also, and what was personally the most surprising and maybe the most captivating thing about this problem, and that we've seen in the video, is that half of this plastic is actually what they call mega plastic. It's big plastic pieces above 50 centimeters. And we've seen that in the video very well with, big bottles, big plastic pieces. It's not only the microplastic we might heard of, or we might, hear about microplastic in our water or things like that. It's also very big pieces of plastic that is thrown away and that you can find in the middle of the Pacific. So this is the problem we're going to look at, which is, can we use optimization to clean up the oceans faster? Okay, so here really the value of optimization is going to be on improving the efficiency of this plastic collection to improve the way they operate this technology that they have developed. So what I want to talk about today is, describe the problem and the key inputs and data we're using in that problem, give you an idea of the flavor of the optimization modeling and algorithm we use to solve this problem efficiently, and most importantly, then show you on the data the Ocean Cleanup has provided us, how big of an improvement in terms of collection efficiency we get, and most importantly, why is it the case that optimization brings sometimes so much benefit. Okay. So as I said, that's what we're going to call the system, or the plastic collection system, a big net dragged by 2 boats. It's going at 1.5 knots, okay? So as they said in the video, it's less than 2 miles an hour, so very slowly. And at the end, it's collecting plastic in this retention zone that's available at the middle. So why is it a hard problem? Well, it's a hard problem because the system has a given length, something like 800 meters currently, maybe 2.5 kilometers in the future. But the GPGP is just enormous, 3 times the size of France. So the system is only covering a very small fraction of the full GPGP. So where you operate is very, very important. Even more so, that density of plastic within the GPGP is very heterogeneous. It's not like a homogeneous mass. It's not like an island of plastic. And so really, it's really important for the system to be at the right place at the right time. And that's typically the kind of situations where optimization would provide most benefit. So here, we're looking at how big of an impact can an optimal steering or routing strategy of the system within the GPGP can have. So the goal is to design an optimization-based approach to optimally compute these trajectories within the GPGP to maximize plastic collection. And in addition, we want to do that in a way where we account for weather and operational constraints. Okay, as you've seen, this is a big system, so we cannot do like drastic U-turns or things like that. So there are constraints on how fast we can turn. There are also more operational constraints. For example, when wave is high, we need to go against the waves, or one that would be important when a wave is height as well, we cannot empty the retention zone. And we'll see that that will play a role later on. Okay. So to answer that problem, the data we use is first data on plastic density. So as I said earlier, the ocean cleanup is actually contributing a lot to the environmental science literature. And in particular, they've built physical models, mostly based on fluid dynamics, to predict the density of plastic in the GPGP. So here I'm only showing you one screenshot of the average density within the GPGP. You can already see some heterogeneity, but think of that as a yearly average, okay? But actually this map is constantly moving over time, right? We also have weather data, okay? So we have data about the wind and the wave. We have the speed or the height of the wave, and we also have the directions, because typically, as I said, when wind or wave is high, we need to go in the direction either of the wind or the wave or against it. So that's, for example, to give you an idea of the wave height in the GPGP over time, over a full year. So you can see here you have Hawaii, on the top right corner you have California. And so you see that, again, this is a very changing behavior. Wave, height is going up and down. Typically, you have more bad weather in the winter. And so that's something we need to take into account, because this is impacting the constraints in our optimization problem. So the approach is to formalize an optimization problem with clear decisions and objective and constraints of optimal routing in the GPGP. So the key decision would be the trajectory. Okay, what's the trajectory of the boat? And as I will describe next slide, we do that by discretizing time and space and describing a trajectory as a sequence of locations. Okay. The second decision is decide to empty the retention zone. Okay, when the retention zone is full, you don't collect anymore. Everything you collect is wasted because it's not stored in the retention zone. But you can decide at any point in time to do this operation of emptying the retention zone. It takes some time, roughly half a day to 1 day, but it's a decision also we need to take into account. And the key feature we're going to use in our algorithm is that the system cannot do sharp turns. So actually, because of that, given a current location and a current steering direction, there's only a very limited number of places or locations I can go to in the next stage. And so that's going to be key in enabling efficient enumeration of all the trajectories. Graphically, how does that look like? Well, here is the current location in red, and let's assume we're moving towards the south. So the current steering direction is going down. Okay, then because we cannot do sharp turns, at the next stage, okay, next time step, there's only 3 possible locations. We can either keep going south, so that means going down again, or we can go slightly west or slightly east. Okay, and similarly, then we can say, okay, what happens in the second stage? Similarly, only 3 possible directions that are just small deviations from the current steering direction. Okay, so basically, if you think about it, going from one stage to another, the number of stages you can go to is bounded. It's bounded by a fairly small number compared to the overall size of the problem. So based on this observation, we're basically going to create a graph, okay, where we're going to have nodes that corresponds to locations at a given time t. So we have all the locations I can be at in the first time period, t equals 0. Then at the second one, t equals 1. Third one, and so on. Okay. And as I said, key is that the number of transitions that are possible, so the number of transitions I can go from t equals 0 to t equals 1 is very limited and very easy to enumerate. Okay, and we do that, and we can construct this graph iteratively. And so here, we're going to construct this graph, and in addition, add a reward to each edge of the graph that essentially corresponds to how much plastic I collect if I go from this location at t equals 0 to that location at t equals 1. Okay, so formulated in this way, you can see that the routing problem, let me maybe have a pointer, the routing problem is equivalent to finding a path in that graph. Okay, so we're going to formulate that problem essentially as a longest path problem where the reward of each edge should correspond to the plastic we collect. Okay. And so why is this, important and actually very impactful in practice is that if you do the math, there are a lot of possible trajectories, okay? As I said, we're gonna optimize over a fixed period. In our case, we're looking at 7 days scheduling by time step of 3 hours. So that's a total of 56 time steps, okay? And a trajectory is simply a sequence of directions, okay? So although there are 8 directions, because you cannot do sharp turns, actually there are only 3, okay? Given a direction, you can either continue the same or change slightly the steering direction. So the number of overall paths or trajectories you get is enormous, okay? 3 to the power 56, that's probably something like 10 to the power 25 or so. If you were to enumerate all of them, it will take many, many years. But by formulating that problem as a longest path, we can do longest path algorithm. And for that, there are much more efficient algorithms to do so, okay? In particular, the algorithm for longest path, they don't depend on the number of paths, on the number of trajectories. They depend on the number of states, okay? And so the number of states, if you think about it, I'm discretizing the space roughly by 100 by 100 grid. And I have also the direction, maximum 8 directions. So at most I have 100,000 different locations, location plus direction, okay? And 56 time steps. So the longest path algorithm is gonna require a number of operations that's only, quote unquote, right, 10 to the 7, okay? So it's still a big number, but hopefully that's something that we can do in seconds, that a computer can do in seconds, okay? So that's why, that's the key idea and key modeling idea is to formulate that as a longest path problem because it dramatically reduces the complexity of the solving complexity and the algorithmic complexity, okay? Of course, we need to, actually we have a bigger problem because we add also the scheduling the extraction decision, but it's still something we can solve at least within minutes. So altogether, we have this modeling of a trajectory as a path in a graph that's describing all the locations at discretized point in times every 3 hours during 7 days. Our objective is maximize the quantity of plastic collected, which roughly will be the same as the longest path if we define properly the reward of each edge. And we can impose constraints as well, okay? In particular, we can, by design, we have the no sharp angle constraints. We can impose constraints that are constraints on the direction you need to go when the wave is high. And similarly, we can impose a constraint, for example, that you cannot empty the retention zone when the waves are higher than 2.5 meters. So in this talk, I'm not going to mention too technical details about the modeling. Just trust me on that. One thing is that we can incorporate the decision of emptying the retention zone while keeping this longest path modeling, okay? Second thing is that we need to be a bit careful about how we define the reward because the reward corresponds to the quantity of plastic you encounter, but this will depend on what you've collected so far, okay? So there's a kind of because plastic is moving, you're moving at roughly a similar speed, you need to be careful about the plastic dynamics and how the past trajectory impacts your future rewards, okay? And so that's what we're able to solve. So here you have a wonderful animation, I really love this one, of a density map, okay? It's above around 2.5 months, going quite fast. And you see the optimal trajectory of the system in that particular case. So you see the optimization really enabling us to capture as much plastic as possible. Actually, if you stare long enough at that animation, and I've spent quite some time being amazed by it, you can see it's quite amazing to see sometimes area becoming, yellowish or even reddish. So showing that some more plastic is getting there and seeing that our system is exactly here at that point in time. So really it's enabling, optimization here is really powerful in helping the system anticipate and making sure that they can be really at the right place at the right time. Okay.
Zan, there's a question. Is it okay if
Go ahead, Dimitri.
It's not mine. It's by in the chat. Aydin says, I get a sense that the most important part of the decision is to choose the initial location and the initial direction. It was not clear to me how you handle that.
Okay, very good question. So regarding the location, actually, we could incorporate it in the optimization. That's possible. It's just increasing the state of feasible location that time t equals 0. However, because we're going to optimize, we're going to do simulations over a long time period, we're going to basically always start from the same point. The reason is that even though we go slowly, it takes up to 2 weeks to go through the entire region. So as far as our simulation is concerned, we're not going to spend too much time talking about the optimization of the initial location. So I would say it's an important problem in practice if your operating time window is very short. But if it's above 2 weeks, probably the initial location doesn't matter much. As far as initial direction is concerned, it is important. Actually, you see in the beginning some very flat lines. That's mostly because of weather constraints and because of the wave height. And that's captured in the optimization. Okay, so the optimization is considering all possible direction at every point in time, including the first one, so as to maximize the entire trajectory. Okay.
Zan, I also have a question, if I may. So the oceans have significant currents that might change the direction of where the plastic can go. Do we have online information about perhaps using fluid dynamic models of the directions of the waves or where they?
Yeah. So we do have some information from physical models. In particular, if you think about the quantity of plastic, you can think of it as following kind of recursive formula. And for every cell in that map, they can tell us the probability that plastic in that cell will go in every neighboring cell. Okay. So you kind of have a transition matrix of the plastic evolution. So that's something we have. However, it's only a model. It takes some physical aspects into account, but not all. So they're typically thinking about maybe having drones around the ship in real time to maybe improve the accuracy of that physical model. But that's actually something we take into account when I said that we need to be careful about the fact that plastic we'll collect in the future depends on the plastic we've collected so far. Okay.
And there's another question, if I may, by Lynn. Can you help me understand what's the impact of weather and other currents distorting the density map is related to what I asked?
So I would say the impact of current and weather on distorting the density map, that's already, I would say, captured in the optimization because the optimization looks at all the future maps. Okay, so the optimization is optimized with respect to the sequence of maps from now until the future, in the future. So it's already optimizing with respect to that dynamics. Okay. However, as you will see, weather will have a very big impact on emptying and the value of optimization, but I'll come to that later. Okay.
Great. Thank you, Zan.
So here, as I said, we're optimizing over 7 days. Okay. But this animation is 2.5 months. So how do we in practice implement that? Well, we have a planning horizon, okay, that's the time we run the optimization. And then there's a implementation period, which is for how long do we follow what the optimization says, okay? And for that, there's also degrees of freedom, okay? We could decide to plan for the next day and follow what the optimization says, then re-optimize for the next day, and so on and so forth. That will give us, a way to optimize myopically, basically, for every day, and do that for as long as we can. So that's what we're going to call plan 1, run 1. Okay. We could do a longer optimization period, let's say 7 days, and we follow what the optimization tells us for the next 7 days. Okay. That's going to be plan 7, run 7. But actually, those two time periods, they don't have to be the same. And so what will turn out to be the most efficient implementation in practice is we're going to optimize for 7 days, follow what the optimization tells us for the first day, and then re-optimize for the next 7 days, okay? and just follow the optimization for 1 day. So that's a rolling horizon strategy. We're constantly optimizing for 7 days, but only implementing for the first day of the PID. Okay, so that's plan 711, rolling horizon. Okay, and finally, we also looked at a folding horizon or shrinking horizon implementation. That's basically doing the same thing, but the end of the planning period is fixed. Okay, that's particularly useful when they need to go back to Vancouver because they're operating from Vancouver. So they might be like, okay, starting on next Sunday, we have to travel back. We need to stop collecting, and they really have a fixed termination point, right? While the rolling horizon is more, in line with optimizing for infinite horizon time of period kind of operations. Okay. So what are the results? So what I'm going to show you is results on 1 year of data that the Ocean Cleanup shared with us. So data about plastic density and weather. And we're going to look at 4-week simulations. Okay, so there are 13 simulations total. And the benchmark we're going to compare with is what they currently use, which is a simple heuristic that looking at all the directions. So kind of similar to what Aiden was mentioning, with the intuition that the first direction is the most important. You just look at all the directions you can go and take the one that seems the best. Okay. And so what we see is that with this strategy, on average, we collect 55.3 quantity of plastic. If I'm not mistaken, this is not tons, but it's proportional to mass. Okay. And this is what we obtain with optimization. So already you see that with an optimization strategy that's myopic, okay, the plan 111, we kind of significantly, so plus 25 out of 50 already, 40% increase in plastic collection. And then we've tried different implementation variants that I've shown you. So the plan 717, the folding horizon, and the best method we have seen in this case is the purple one, which is the rolling horizon. And so what's very, I think, impressive and exciting about this project is that we really see here the value of optimization with almost a 50% increase in collection yield for plastic collection. And that's important because, if you think about it, that's directly impacting how much it costs to remove plastic. It's an NGO, so they're not trying to make a profit out of it, but the lower the operating cost, the more they can operate. So they can reinvest that money in having more systems. It can also make it more competitive for companies that want to subsidize those type of collection, maybe to improve their overall footprint. So it's really impacting a lot how valuable and how viable this type of plastic removal and plastic cleaning strategies and projects are. Okay.
Zan, there's another question, if I may.
Yeah, go ahead.
By Karen, what about refueling, restocking the ships and emptying all the collected plastic? How is that incorporated in the planning?
So, good point. Refueling currently not, okay? So currently we're not taking into account refueling. However, we are taking into account emptying, okay? So when we decide to empty, basically in the model that leads to 1 day where you don't collect any plastic and where all you do is emptying the current system. So potentially we could think that this is also giving you a time window when you can refuel the ships, okay? I must say that this is also part of a broader discussion they have at the Ocean Cleanup of maybe not having 2 ships, but having 3 ships with a new ship that's replacing one. So you will not need refueling, but you can actually constantly change the ships, change also the crew, because that needs to happen. So it's a very good point. There's a lot of interaction of this operational steering model with a more strategic or tactical one of crew optimization and fleet management. And hopefully having an optimization model helps us connect the two. But so currently we're scheduling for the extraction. It's 1 day when you don't collect plastic, but we're not taking into account refueling, but potentially that could happen during that time window, that same time window. Okay. Especially because, as you saw in the video, when they extract the plastic, they need another ship, okay, a mothership where they put the plastic they've collected. So this ship potentially could also come with a refueling ship, or could come with other resources, foods and things like that for the group.
There's one more question.
Yeah,
you can stop me if you feel we are, but it's a good sign actually. so Fabio asks, returning or not to a location might be influenced by the fact that the plastic has already been removed or not at that location. Is this taken into account?
Yeah. Okay. So yes, it's taken into account. So that's what I was referring to about taking into account the plastic dynamics. So maybe if I go back to the great, actually I can do that faster. Oh. If I go back to the great GIF animation, when the system encounters a big red hotspot, this hotspot no longer moves, okay? So we take into account the fact that this plastic has been collected and no longer moves and it no longer propagates. So we take into account what you mentioned, Fabio. In other words, when we go back to a location, we don't count the plastic collected twice. However, when I say when we go back to one location, we have to be careful because plastic moves too. So to be precise is when you supposedly see a piece of plastic you should have seen in the past, okay? Maybe it's not exactly at the same GPS coordinates, but it's seeing again the same piece of plastic. So we account for that. And the rewards I'm showing you, so the numbers I'm showing you for every method is taking that into account, okay? So we're not double counting the pieces of plastic you might have seen in the past, okay? So, you know, we're very happy about the results, and what we wanted to know is get a better understanding of why optimization is so powerful. What is the key feature of the problem that optimization enables us to do very well compared to the benchmark, okay? And so to get a sense of that, we actually stratify the result by season. So those are the same results I showed you, but only on the winter, okay, January to March. And you see that in this case, the benefit for optimization is actually much higher, above 90%, okay? When you look at the summer month, the picture looks very much different. The improvement is only 30% gain in efficiency, okay? So here we see that first, overall plastic collection is harder in winter, okay? The numbers I have here for all methods are much lower in winter than I have for summer, but the benefit from optimization is much greater. So that's the best news you can hope, right? Because you don't want optimization to help you when the problem is easy, right? And this is actually showing you, okay, in winter, it seems to be a harder problem. And in winter, this is where the relative benefit of optimization is the greatest, okay? So another way to say the same thing is here on the x-axis, you have month. On the y-axis, you have the reward we get for each method. And you have this kind of nice inverted U shape that shows exactly what I told you. Rewards, so plastic collected is lower in winter, and the relative benefit from optimization is greater in winter. Okay. So we asked ourselves why. Okay, why is it the case? And the short answer is weather. Okay, in particular, constraints about emptying and wave height. As I told you, you cannot empty the system when the wave is too high. And this is because optimization is taking that into account and is jointly optimizing for the trajectory and the scheduling of the emptying. That's why we get most benefit. So the best way to get convinced of that is to look at another picture, which is the average wave height in the GPGP according to month. Okay. And personally, when I look at that picture, I'm like, okay, there must be a connection between the two. You take the left, you flip it, you have the right. Okay. So clearly, there's something about the wave height that we do particularly well. And I think the key thing is that optimization is taking the wave height into account when looking at emptying. Okay. So more precisely, and I think also that will answer some of Karen's concerns. Here, what you see, for example, on the x-axis is time, okay? And you see the profile across 4 weeks, 28 days, of the plastic in the retention zone. And so you see, as you collect, plastic increases, you reach capacity of the retention zone, you wait a bit, and then you empty for a day. So you have 1 day where you are at the lower level, and then you start emptying again, okay? And so what you see is that because it's not possible to empty when the wave is high, there are some periods, especially in the winter, where you just wait, okay? Either you wait for the weather to improve, or you just move away from the high wave region to be able to start the extraction, okay? And so the key thing is that the optimization that jointly optimized for trajectory and emptying just does that in a much smarter way. Okay, so you see that it empties way more often, and in particular, sometimes it's emptying before reaching capacity. It anticipates. Okay, and in particular here, you see it's emptying at this region, even though it was not completely full, while it's probably just before the high wave point. Okay, so that's, I think, one of the reasons why optimization is so beneficial in this case, is that in addition to really taking into account the time component and the plastic dynamics, it's also jointly optimizing for collection and emptying, and that's proved to be very effective, especially when emptying is a very important constraint. So especially in the winter month, where the window to empty because of wave constraints is very tight. Okay.
Then there's another question by Alex. The question is about multiple SIPs, multi-SIP coordination. Are we leaving optimality on the table by treating one SIP at a time, or is the mother SIP routing problem comparatively easy?
Okay, that's a good point. So short answer is currently they don't know how they're going to operate the mothership. Okay, so actually, as they explained in the video, currently, because the system is small, what they do is they put the two ships together and they empty on one of the two. And they're starting to experiment with the mothership business. Okay, but that's a very good point about what do they do in the mothership, and if they have multiple systems, which they want to do, they want to have, you know, up to 10 systems. To what extent they're going to share motherships? Okay, that's a very good point. And our hope is basically that having an optimization model for the routing of each system will enable us to help them answer those questions. Okay, and actually we already kind of can, because also by doing this, we can be a bit more precise, and we can tell them a bit more precisely how often do they need to empty, right? So, or things like that, more, you know, reduce idle time, which is basically idle time here. So hopefully we can help them inform those decisions of, okay, if you see you need to empty every 2 days, one mothership for multiple systems is just not possible, right? So I think we're at a stage where they're starting to use the model also as a way to inform those more high-level tactical or even strategic decisions, okay? And actually, so that's a great transition for another example of strategic decision is capacity dimensioning, okay? So because we've seen that emptying is so important, because emptying is basically a fixed cost. Once you're full, you have to wait 1 day to empty. What we can do using our optimization approach is to play around with the different parameters, how big the system is, how big the retention zone is, how long does it take them to empty the retention zone, and give them an idea of what's the impact on collection efficiency, because most likely this impact is actually nonlinear and not super intuitive, okay? So using this simulation and this optimization engine, we can produce those kind of heat maps, where here on the x-axis, you see the time it takes to empty the retention zone from 6 hours to 2 days, okay? And on the y-axis, reverted, the capacity, okay? How big the retention zone be. So here, using that, they can start to, you know, inform their decision and discussion about, should we innovate on how we empty the system, okay? How big the motherships needs to be, because maybe to have 10 tons of plastic, it's probably fine to have, you know, a small motherships. 100 tons is probably, you know, a massive cargo. So we can actually use also optimization, not from a purely operational perspective, but also to inform those strategic kind of decisions about where to focus their effort. And as I said, because they're thinking about moving from 800 meters to a 2.5 kilometer wide system, I think they're also asking themselves the question of, should we scale proportionately the retention zone? Okay. And I think this project has been extremely helpful for them to realize, you know, that if they're actually, that the way they're collecting is currently quite inefficient. If they improve this efficiency, actually the size of the retention zone is going to become a major bottleneck, way more than the size of the system altogether. Okay. So here, most likely, in this graph, what's most likely is that you move along an anti-diagonal, right? If you want to decrease the time it takes, you probably need to also decrease the size of the capacity of the retention zone. But hopefully there are, innovative ways. So maybe using 2 motherships instead of 1 that are, ways to artificially kind of reduce empty time or things like that. Okay. Typically, if they use a mothership, they don't need the mother. They can start collecting, even though the sorting on the mothership is not done, right? So if they use a mothership, they can decouple, emptying the zone, the retention zone, and sorting the plastic so that it can go into recycling. So that's the kind of thing they're currently thinking about, because also from their side, it's an R&D project. They're constantly developing the system, trying to improve its efficiency. And so there are a lot of decisions that they're trying to figure out as we collaborate with them. Okay. So to wrap up on that, key takeaway of this project is that thanks to optimization, because we have this nice graph-based formulation, we're able to find efficiently one of the best route in a simplified case, but in general, one of the best route, even though there are 10 to the power 26 trajectories in theory, in a few minutes, okay? And that really is the main contribution and benefit of this work, is enabling them to sort through all this complexity in a very computationally efficient time, okay? It's an optimization model that allows them to formally put plastic collection as an objective, and all operations and weather-related constraints as formal constraints. So it's also enabling them to have trajectories and planning that is closer to being feasible than what they currently have. And it leads to a yield improvement in the 30 to 80, 50 to 80 range. Again, as I said, depending on time of the month and how binding basically the wave constraints are. Okay. And so as we're moving forward with this collaboration, key steps we want to include is first include and protect against some uncertainty on the plastic density model, also the weather data that we get, and potentially also develop some more adaptive strategies that would adapt the trajectory or the planning based on real-time information they might gather. So as I said, they're thinking about having drone images, also potentially having GoPros on the ships to scan the plastic, because one of the tough things is that those plastics typically don't appear on satellites. So, or at least not in a visible spectrum. I think they're looking also into other wavelengths. So, so there are a lot of also opportunities to get more data, more real-time data, and have potentially a more adaptive steering strategy in the future. So with that, thank you very much for your time, and I'm happy to answer any remaining questions.
Zan, I have a question, if I may. In terms of very exciting work, I preface it by that. But in terms of, in the end of the day, there's a lot of plastic in the oceans. In order to actually make a dent on the problem, do you have a sense of what is the size of activity, how many vessels, how many, what is needed to actually really address significantly reduction of pollution, plastic pollution in the oceans?
So two things. One thing is interception. Okay, so if you think about it, as I said, it's 8 to 10 million tons per year being thrown in the ocean. 2 tons out of those, so 20% of those through rivers. Okay, so very efficient thing to stop this problem from getting worse is interception, and that's also something else they're doing. But I would say in terms of analytics, it's probably easier. You have a barrier at the river, at the end of the river, to try to collect plastic, just downstream rivers after all the industrial sites or things like that. It's one way to address that. So I would say there are also interception or reducing plastic waste to start with is a very, very efficient way to prevent the plastic pollution problem from growing. Then to answer more specifically your question, what they've estimated with the steering strategy they've had in mind, right, is that with 10 systems, it will take them 10 years to remove half of it for the GPGP.
I see.
Okay, that's estimate based on the steering strategy they were thinking about, not taking into account all the inefficiencies that might come up from operational constraints. So I think we could improve the steering strategy to make that happen faster. We need also to take into account a lot of operational issues that might happen. But actually, I was very surprised by this number, because if you think about it, 10 systems, 10 years, half of it is quite substantial. And it's diminishing return, because then as you remove plastic, you have to operate on the less dense areas, and currently it's growing 2% per year. So that's why my first point, also dealing with the problem growing, is also a very efficient way to do it.
Great, thank you. Other questions?
I see a raised hand. Go ahead, Lynn.
Hi, everyone. Thank you so much for providing the overview. That was very exciting. I was thinking this about like in a similar direction in terms of scale and opportunities of scaling it up. And I'm just curious whether there could be a synergy to commercial shipment companies that anyhow would cross the Pacific garbage patch, and whether there's a model which could scale the cleanup operations and provide an incentive for commercial operators to, as they're anyhow transporting goods from coast to coast, to then also get involved in the cleanup activities, and how a policy around this one could look like.
Yeah, no, that's a very good point. So what I know about those potential synergies at the moment is that Maersk is a partner of the ocean cleanup. So a lot of the ships actually they're operating are provided by Maersk, so the shipment company. And they're thinking, when I was talking about gathering real-time information, for example, they're thinking about maybe using the ships from Maersk and put sensors like camera on those ships, even though they're not collecting plastic, as a way to gather information and have more accurate information on local plastic density. That's a very good point, though. Could they do even more and try to use those ships for the collection directly? That's a very interesting point. I have personally no idea whether that will be feasible, and whether the routes they're taking are actually the most high density routes. But that would be a very very exciting synergy, actually. Yeah.
Any other questions? Zan, I have another question myself.
Okay.
So the algorithms really depend on how accurate the probability, as well as the rewards are, that I suspect are estimated using fluid dynamic models.
Yeah.
Do you feel that that uncertainty is a first order concern or a second order concern? In particular, I'm thinking, would taking into account this uncertainty might be even more helpful?
So I think that so actually there's uncertainty on the probabilities and on the weather.
Yep.
So I would say that given how important weather constraints are on the bottom line, especially in the winter, I would suspect that would be a very important one, because if you think about it, weather constraints make the problem feasible or not feasible. So it's really a feasibility issue. And if you think you can empty and you cannot empty, your reward is zero, basically. You cannot collect anymore. So I would think that uncertainty might be in my intuition would be that this uncertainty might be the first order issue. Then about the plastic density and the fluid mechanics, I think it's also an important source of uncertainty. I think there's also, implementation errors in, following exactly the right steering angle and steering direction. So my kind of hope, at least, is that the uncertainty on where the plastic is could be canceled out by the uncertainty on what would be exactly implemented. And that, at the end of the day, captain of the ship will be able to slightly deviate to be closer to the plastic, right? So I think overall, if we get the high regions right for plastic density, I think the overall trajectory is quite good. Right?
Thank you very much, Zan. I would like to pass it to Dick. Thank you. Dick?
Yes, so I'd like to announce that the next webinar is in fact not a webinar, but a conference. So that's on May 24. So then we have an Analytics for the Better World conference, and that is the whole afternoon. But you will certainly receive also information about that. So we have, I think, in total of 4 or 5 hours with many interesting speakers and contributions. So that's on May 24. So that is the conference that replaces the webinar. Thank you.
Thanks, everybody. Thank you, Zan.
Thank you very much, everyone. It was nice to see friendly faces.